We spent the beginning of this unit talking about exponentials. We then had a short pause talking about inverse functions so that we could talk about exponentials since they are the inverse. So we could talk about logarithms since they are the inverses of exponentials. So since they're inverses, a lot of the properties are going to be really similar. So we're going to go through the properties of a logarithm the same way we went through the properties of an exponential at the beginning of the unit. So to begin, a logarithmic function has the general form that's listed here, where you could potentially multiply something in front of the logarithm with a base b. That base b is always going to be greater than 0. It's not going to be a negative number in the base. And a and b both cannot equal to 1. Okay. Now there are two ways that a logarithm might look for most problems that we're going to see here. You have your first kind of logarithm where, let's highlight, the a is greater than 0. That means that the number in front of the logarithm is a positive number, so we have not reflected it across the x-axis if we think about all of our transformations. And the graph goes from negative infinity to positive infinity, increasing. If we somehow flip around that a value where the a value is negative, it has reflected over the x-axis, or we're multiplying by a negative number in front, so my logarithm itself flips over. This is a reflected version of a logarithm. So this is like normal shape. This is a reflected shape. Either way, the range of this function has been from negative infinity to positive infinity for both graphs. So here's a fun fact for you today. The range of a logarithmic function will always be from negative infinity to positive infinity unless you are specifically cutting it off at certain input values. So if you are told this graph only shows up from 3 to 5, well then yes, you will have maybe a maximum or minimum. But a typical unbounded function is going to go from negative infinity to positive infinity. The thing that we do need to recognize is that the domain is not all real numbers. For both of these graphs, where do they start? 0. Now, this is really specific for these graphs. They don't technically start at 0, though, because what kind of endpoint do I have on this domain? Is it a bracket? No, it's a parentheses. Parentheses means we don't actually touch that number, but we get awfully close. What that means for us is that there is a vertical asymptote on both of these graphs at 0. The logarithm is going to get insanely close to, infinitesimally close to that vertical asymptote, but it will never actually touch it. So our domain starts just after 0, but like minutely after 0, and then goes to infinity. So as long as when you're telling yourself it starts at 0, air quotes, you're meaning but not including 0, that's an okay thing to tell yourself. Starts at 0 but doesn't include 0. Now some more characteristics here. Just like an exponential, a logarithmic function is always going to increase or always going to decrease. It will never switch from increasing to decreasing like our quadratic or like our polynomials, which means you will not have any local extrema unless, again, you chop it off at some closed interval. And since it's always only increasing or decreasing, it's also always only concave up or always concave down. Now, if we think about what that looked like, remember when I taught you this, I had you hold your hands in front of you as either concave up or concave down. That's still going to exist, and you will only have one of these two options for the entire graph. It will never switch from concave up to concave down, which means that there are no points of inflection. So this is very similar, again, to our exponential characteristics because, again, they're inverses of each other. But the end behavior for a logarithm is weird. We already talked about how it doesn't actually go from negative infinity to positive infinity on the x-axis. So when we talk about end behavior, we're not talking about limits to both of the infinities anymore. Since logarithmic functions have a restricted domain, starting at 0 but not including 0. They are vertically asymptotic to x equal to 0. That's why we graphed that vertical asymptote. As a result, the left end behavior will occur as x approaches 0 from the left side. We need to highlight this right here. Typically, when you wrote end behavior, you wrote it as x approaches positive infinity and x approaches negative infinity. We don't even approach negative infinity, though, because there's a boundary at 0. So instead of saying negative infinity for the left side, you say 0 from the positive direction. Okay, that superscript of plus has to be there because you're saying I'm looking at 0 from the right side, from the positive side. So your options for what end behavior as a limit statement might look like are the following. Again, this top one is for when a is greater than 0, so our positive graph, our increasing graph, that's concave down. If you look on the left side, as we get close to 0 from the right, not negative infinity, this graph is going down. So we would have an end behavior of negative infinity. As we go to the right, though, our graph is slowly going up. It looks like it's going to flatten out, but that's not true. That's a mistake for your eyes. It's actually going to keep going up and out for forever. So as a note for yourself, let's make sure we know that this is talking about the left side of the graph and that this is talking about the right side of the graph. X approaching infinity has always been the right side. But for logarithms, since we don't actually get to negative infinity, we don't say negative infinity on the left side. We say 0 from the positive. If we switch that around and now we have a reflected graph, so a is less than 0, again, this is what my reflected graph looks like. On the left side, my graph is going up. So again, when we do our left side end behavior, it's going to be going to positive infinity. And when we do our right side end behavior, since it's going down, it's going to go down to negative infinity. So the rules are essentially still the same from how we've done end behavior. The main difference is this left side not going to negative infinity, but going to 0 from the positive side. We're approaching 0 from the right. Okay, all of this information is kind of what we're dealing with today, just talking about these characteristics for the logarithmic functions. So let's start with what is probably the most tricky. Let's write some limit statements for our end behavior. Okay, I've given you kind of a footprint here for the first one. For the graph of f of x in problem A, we want to do the left side end behavior. Notice I already wrote it for you because the left side is the weird one. But on the left side of this graph, what is happening to my y values? They're going down to negative infinity. On the right side of this graph, that arrow is headed up. So we would say the limit as x approaches positive infinity for f of x, that's the right side, would be equal to positive infinity since that arrow is going up. For h, this is a reflected graph, so we can see that on the left side, that graph is going up, and on the right side, that graph is headed slowly down. So to write the left side end behavior, we don't say to negative infinity anymore. We would say the limit as x approaches 0 from the right of h of x would be equal to positive infinity. And on the right side does not change. It's not weird for this kind of graph. It's x approaching infinity because the x's are going off to infinity. For h of x, this reflected graph would have it go to negative infinity. Now, just like we did with exponentials, so obviously we can do end behavior from a graph really easy. We can also do end behavior really easily from an equation without graphing it. All we need to know is what the a value is. What's the a value here? 2. So a is going to be greater than 0 since 2 is bigger than 0. That means this has not been reflected. And if it has not been reflected, then the logarithm itself looks something like this. This is a typical logarithm that has not been reflected. It's going to be growing. And now that I visually know what it looks like just from that a value, we can do our left and right side end behavior. Again, on the left side, we do a limit as x approaches what number? 0 from the positive side. This is g of x. And what is that equal to? As we look on the left, so from the blue graph, as we go to the left, it gets close to 0. Where is that y values going? Negative infinity is going down, so negative infinity. How about the right side? What are we approaching on the right side? Positive infinity, heard it. And our arrow's going up and off screen, so this is to positive infinity. Questions about limit statements before we move on? This is probably like the 8th time we've seen limit statements so far. We're going to continue to talk about them every time we introduce a new function. On the back, we need to talk about some other vocabulary. So again, these characteristics: increasing, decreasing, and concavity. So for part A, don't think too hard about this. Is this logarithm increasing or decreasing? Decreasing. Now maybe think a little harder about this. Is this concave up or concave down? Concave up. If we were to do our hands with this one, it would match a concave up hand. So this is decreasing, but concave up. What about B? Is that increasing or decreasing? Increasing. Now based on your hands, is that concave up or concave down? Concave down. Ooh, interesting. Now again, part C, I didn't give you a picture, but all we need is the A value. What's the A value here? -4. So my A value is less than 0, which means if we were to sketch this really fast, it wouldn't be increasing, it would be decreasing. So this is a decreasing, what kind of function? Concave up. Now, as a reminder, because I know you've forgotten this, when we're talking about concavity, we're talking about the rate at which it is increasing or decreasing. So as a note for yourself up here, remember that concave up means that it's increasing at an increasing rate. And when we're talking about concave down, we're talking about the rate at which it's either increasing or decreasing, happening at a decreasing rate. When we did polynomials, this made a lot of sense because the graph was going up and down over and over again, so we saw how it was changing faster or slower, increasing rate or decreasing rate. But now with exponentials and logarithms, it's a little bit more difficult to see. So don't forget that when we're talking about concavity, we're talking about the rate at which the graph is changing, not like a slope. Example 3, the first couple questions here are really simple and then it gets really thinky. So hang on with me for the last couple examples here. It said selected values of several logarithmic functions are shown in the tables below. For each table, find the value of the constant k. So in case you didn't actually notice this, there's a missing term here in the table. We need to figure out what it is. The nice thing is we've been told these are logarithmic. We can tell that they're logarithmic because the x values are multiplied by some number and the y values are added or subtracted by some value. So if we know that, what is the pattern happening in my x values here to change from number to number? Times 2. I think I heard that. So if we know every single one of these needs to be times 2, what is k going to be equal to? 4. Easy peasy, yeah? Y'all got the second table. I want y'all to try those. I want you to find me the value of k. So again, since we know that these are logarithmic, and I'm verifying they're logarithmic by noticing these are multiplied by some number and these are just adding 5 every time, what number am I specifically multiplying for each of the input values? Well, we can't really tell from the first bit, but if we look from 6 to 18, that's times 3. 18 to 54 is times 3. 54 to 162 is times 3. So what's k? 2. Now that's too easy, because that's just pattern finding. So let's kick it up a notch. This time, if I'm looking at the table, I know k is here. Following the same thought process, I would just try to figure out how these numbers are changing. From 4 to 5, 5 to 7, 7 to k, and k to 19. Well, It's going to be a fraction, and it's specifically the second number divided by the first, the second number divided by the first, the second number divided by the first, and the second number divided by the first. Are those all the same fractions? No. Okay. When we did this with exponentials, we had to start thinking of how these numbers could change if we added or subtracted a number to then cause the multiplication to happen. So we got to get thinky. Does anyone recognize a pattern that this is close to if we add or subtract a certain number of values to the input values? It's tough. If we just start with some of the basic exponentials, meaning we're thinking about 2 to the x, 3 to the x, and 4 to the x. That means I'm multiplying by 2, by 3, or by 4 every time. Just those are simpler numbers to use. 2 is 1, then 2, 4, 8, 16. Are these numbers semi-close to 1, 4, 8, 16? 1, 2, 4, 8, 16. I just knew I was missing a number. If we try to make these 1, 2, 4, 8, and 16, what would I have to subtract from each of those input values to make it that pattern? 3. Okay, so you're saying that if I take the x value and subtract 3, then that's equal to 2 to the x power, which means I'm multiplying by 2 each time for my adjusted numbers. So what's k? If this pattern has it being 8, 11. Did somebody say 11? I just didn't hear you. This ear is plugged today, so I cannot hear you unless I turn that direction. Sorry. This is tough, yes.
Did you plug in 8 into the x?
This is a misleading equation now that I'm writing it like this. So the x input value minus 3, the input value that I'm using, would be, minus 3 would be in the pattern x to the second power. What? 2 to the x power. So it's not like I'm solving for x or something. I'm just thinking, okay, if I want this to be 8. Okay, I want this to be 8. But all of these numbers are 3 more than this, yes? 1 to 4 is plus 3, 2 to 5 is plus 3, 4 to 7 is plus 3. That means this has to be what? 8 plus 3, 11. It's like, I know, it's really thinking, and there's not a lot to put down on paper to solve by hand. You just have to think about patterns. Let's look at the next one, because I think I kind of blew your mind with that one. We'll calm it back down. So with this one, again, my output values, L of x, are changing by plus 7 every time, so I know this is going to be logarithmic. But I just got to figure out this pattern so that I can figure out what k is. What do you notice about these problems? They're all base e. They all have exponents. One of them is invisible. What's this exponent here? 1. Okay, so if we think about the exponents and how they're changing, maybe specifically looking at this one so we can get rid of the negatives. How do you go from e to the 7th to e to the 10th? You said plus 3 because you're talking about the exponents, right? So in fact, what am I multiplying by to make an exponent plus 3? E to the 3. E to the 7th times e to the 3 is e to the 7 plus 3, which is e to the 10th. Ooh, our exponent rules. So if we multiply each of these by e to the 3, what does that mean k is equal to? E to the 4th. Okay, we've discussed this last little bit before. There are 3 functions that have restrictions on their domain. Every single other function has a domain of all real numbers. These 3 do not. We've already studied rational functions. Remember, rational functions are fractional exponent or fractions with x values in the denominator. The restrictions were that x could not equal to 0. So in interval notation, this was from negative infinity to whatever was down there causing the denominator to be 0 and pick it back up right after. Square root functions you studied in Algebra 2 and we've discussed a little bit here. What's the restriction on a square root function? What can you not take the square root of? A negative number. So we say x has to be greater than or equal to 0. In interval notation, that's from 0 to infinity. Logarithms is what we're studying now. In a logarithmic function, whatever is in the argument or inside the logarithm, based on what we noticed on the front side of this page, has to be greater than 0 because you can't touch 0 and you can't have a negative value. That's what we saw in our picture, which is where we get this domain of 0 to infinity with the parentheses on both sides, not including 0. Now that's fine and dandy, but the amount of times you're just going to have a plain x inside of a logarithmic function is very slim. So you are going to have to solve for a different type of domain. It's not always 0 to infinity, but there is some restriction. What I mean by that is you are going to take the argument, which is the stuff inside the parentheses, stuff inside the logarithm, and you're going to set it up just like this. Whatever's in there, greater than or equal to 0. Once you solve for that number where it says x greater than or equal, sorry, not equal to, greater than some number, that's the number that goes in your interval notation here. So what I mean by that is, in example 4, to find the domain and range, we first highlight or notice what is in the argument, which is in the parentheses, x plus 5. Well, that x plus 5 is what is not allowed to be greater than, or has to be greater than 0, sorry, cannot be equal to 0 or less than 0. Can we solve that for x? It's just like a one-stepper. Subtract 5 from both sides. You get x greater than negative 5. So that number, negative 5, is what goes into my domain. This goes from negative 5 to infinity. That's the domain of the function. Did we follow? So whatever's in the parentheses, set it greater than 0, solve for x. That's your number that goes at the beginning of your domain. The range for a logarithmic, we never have a restriction on. Remember, it's the inverse of an exponential. Since exponentials have unbounded domains, logarithms have unbounded ranges. So that should be an automatic answer, unless, of course, you're chopping it off at specific values. For part B, what should I highlight as part of my restriction? X minus 3. Okay, that's what we're trying to solve in my little bitty inequality. So x minus 3 greater than 0. Real quick, we add 3 to both sides. This is x greater than 3. Which means we are saying the domain is from 3 to infinity, because it's where it has to be bigger than 3, from 3 to infinity. Now, a great question I expect somebody might have is like, wait a minute, Miss Quigley, this graph has been reflected over the x-axis, so we're worried that something could potentially happen to the range. I see that, but remember, our range goes for our logarithm goes from looking like this to looking like this. The range has not changed and will not change. It's still from negative infinity to infinity. So those reflections over the x-axis don't affect my range at all. What should I highlight in this one to be a part of my domain? 2x plus 3. Now this is a two-stepper. We have to solve 2x plus 3 greater than 0. But we've been solving two-step inequalities since like 7th grade. We subtract 3 from both sides. We divide by 2 on both sides. Do I need to flip my inequality sign? No. When do you flip an inequality sign? When you're dividing or multiplying by a negative. When you write the negative number down. which means that this domain is going to go from -3/2 all the way to infinity. And the range, again, automatic answer from infinity to infinity. How does that feel? So its characteristics are things that we've talked about with other functions. We're just applying it now towards logarithms because they have some interesting characteristics. To practice this today, I need a whole bunch of things to happen. So listen to all my instructions first, and then I'll actually explain what's going on.